What we've been doing has been called the binomial theorem. And I know we are introduced to an example before, we'll do a couple more examples. We'll look in our textbook at the formula that's given here, and we'll also introduce you to a formula that your formula sheet has. But what the binomial theorem says, and we'll color code things here, we have Pascal's triangle, and the numbers in Pascal's triangle relate to combinations. So we've seen that this is 4 choose 0, this is 4 choose 1, this is 4 choose 2, 4 choose 3, and 4 choose 4. So when we're expanding something like x plus y to the n, Pascal's triangle become the numbers in front. So I'm going to underline them here in blue. And you start with, if you were doing row 5, you would start with 4 choose 0, then 4 choose 1, then 4 choose 2. And whatever your exponent is tells you which row to use. Okay? There's always, this is an important note to make, there's always n plus 1 terms in the expansion. So if the exponent was 3, there would be 4 terms. If the exponent is 4, there would be 5 terms. And then if there's 5 terms, you know you have to use the 5th row of Pascal's triangle, which has 5 numbers in it. So first of all, that's your leading coefficient. It comes from Pascal's triangle. Then within your binomial, you have a first term, which I'm going to underline in green, and a second term, which I'm going to underline in purple. Now, your green term, whatever your first term is, you're going to have x to the n of them first, then n minus 1 of them, then n minus 2 of them, then n minus 3, and you keep going down until you have none of them left. So if the exponent is 4, you would have x to the 4, then x to the 3, then x squared, then x1, and you go down until you have none of them left. With your second term, you start with none of them. The second term has 1 of them, then 2 of them, then 3 of them, and you keep going up until you get to all n of them. So this is how the pattern and Pascal's triangle works. And we're going to do, I know that you've been working on the examples already, but we'll do another example together just to see how that works. So here we have expand and simplify 4a squared plus 2b to the exponent of 3. So when I'm looking at Pascal's triangle, I would only need to go to this 4th row, because that 4th row has 4 terms, and because my exponent is 3, I know that the expansion of this is going to have 4 terms. And I already know that the coefficients, which I'll do in blue, go 1, 3, 3, 1. My first term is 4a squared. I'm going to underline that in green because I would start with 3 of them, then 2 of them, then 1, and finally none of them in my last term. My second term, which I'm going to do in purple, the 2b, I'm going to start with none of them, then have 1, then 2, and finally 3 of them. Plus signs between each of my terms. To simplify this, I'm going to simplify it in 2 steps. We're going to simplify all of our exponent laws first, just like order of operations. So I'm going to keep the blue 1 here. I'm going to have 4a squared cubed. 4 cubed is 64. A squared cubed would be a to the 6. plus 4a squared squared will be 16a to the 4. And simplifying my purple one, well, it's just going to stay 2b. Now the purple one is getting squared. And finally, 2b cubed will be 8b cubed. Once you've simplified all of your exponents, now you can just multiply your coefficients together. 1 times 64, that'll be 64, a to the 6. 3 times 16 is 48, times 2 is 96, a to the 4b. 3 times 3 times 4, 36, a squared b squared. And finally, plus 8b cubed. So this is how the pattern and Pascal's triangle can be used to find this. Now on your formula sheet, you don't have, like in your textbook, excuse me, in your textbook they give you this complete expansion. Your formula sheet does not have that. What your formula sheet has is the following formula. It says tk plus 1 equals n choose k, a to the n minus k, b to the k. So what I have in this blue box here is what's on your formula sheet. What does this mean and how do we use it? Well, the first thing that you need to know is that this finds a specific term when you're expanding a binomial that looks like this. So the a stands for our first term, the b stands for our second term, and the n stands for our exponent. But that's not on your formula sheet. So you will have to remember that the a stands for your first term, the b stands for your second term, and the n stands for your exponent. And what this formula does is it finds specific terms. So let's say we want to find this 96 a to the 4b. In the complete expansion, does that make sense that this is going to be our second term? This is our first term, second term, third term, fourth term. And if we wanted to find term 2 with this formula, that immediately tells us what the value of k is. So the value of k changes depending on which term you're finding. But if this formula finds term k plus 1, if I'm finding term 2, does it make sense that k is equal to 1? Because 1 plus 1 would give me term 2. I'm going to color code things the same way I colored things before. So the n choose k, in this case, because the exponent is 3 and k is 1, I'll write that in blue. 3 choose 1. A to the n minus k, I'm going to do that in green. The first term in my expansion was 4a squared. N minus k would be 3 minus 1. And my b, which I did in purple before, I'll do in purple here as well, is 2b to the 1. Now 3 choose 1 is 3. Here we have 4a squared, 3 minus 1 would be squared, and here we have just 2b. And you'll notice that what we have as a specific term matches up perfectly with what we had right there. The 3 comes from Pascal's triangle as the coefficient. 4a squared squared because of the pattern going down by 1 and having 1, 2b. So what the formula does is instead of having to expand everything, it can find a specific term. And just like before, you would do your exponents first, so this will become 16a to the 4. And I would leave this right now, and then once your exponent rules are done, multiply your numbers, multiply your variables, and we get 96a to the 4b. So you could use the formula 4 times if you wanted to do the complete expansion. You could find term 1 with the formula, then k would be 0. We found term 2 with the formula. You could find term 3 with the formula, then k would be 2. You could find term 4 with the formula, then k would be 3. So the formula allows us to find specific terms if we want, but usually if the question is asking for a complete expansion like this, using Pascal's triangle and the pattern seems to work the fastest. So you can continue working on the ones from this morning and add number 7 to that just to practice expanding completely.